All right, continuing in Chapter 2, Section 6, we've looked at domain restrictions. The next objective is to look at combination of functions, the combination of functions, and also composite functions. So right here where you see the algebra of functions, that means that we're going to be doing combination of functions. So functions can be combined using addition, subtraction, multiplication, and division. I think what trips people up is the notation. Okay, this says that if we have two functions, f and g, f is one equation and g is the other, and they're two functions, then the following notation applies to combining them. So if I want to sum f and g, I could write it as either f plus g in terms of x. This doesn't mean multiplication here. This just means that f and g both have an x in their equation. For example, down here for this first example we'll get to in a minute, this is f of x, which just means that this x right here tells us that, hey, watch out, what's upcoming is that there's an x in the equation. And g of x also that we might see an x in this equation. This very well could have been f plus g of r, then this would have had to have been f of r and g of r, which just means that the r's would have been present in the equation. That's all. So the two different types of notation that tell us that we have to sum and combine f and g is f plus g in its own parenthesis in terms of x. We might also see it as just f of x plus g of x. The difference can be written similarly, where we have f minus g with the x outside, or we could just do f of x minus g of x. So these different notations mean the same thing. So how do we know we need to multiply two equations together? Well, f times g, that's implied multiplication, or f of x times with the multiplication dot times g of x. How do we know to divide, to find the quotient? We do f divided by g of x or f of x over g of x. As long as, remember, for domain restrictions, the denominator g of x cannot be 0, whatever that equation is. All right, so the domain of the new function after you combine by summing, subtracting, multiplying, or dividing, the domain of the new function is the intersection of the domains of the original functions. And we'll just kind of look at that intuitively. All right, so for example 1, notice that they say, okay, let f of x be this equation and g of x be this equation. And they want us to find the sum, difference, product, and quotient, and they want us to determine the domain. Well, since the domain of the new combination is the intersection of the domains of the original functions, it'd be good to get the domains for both these polynomial functions. These are polynomials. There's no fractions or radicals, so we know the domains are all real numbers. All right, so for example 1, given f and g, they want us to add f and g together. So these are the same notation, the notations that mean the same thing. All right, so I'm going to use this space down below. Okay, so I'm going to find f of x, which is 3x minus 4. Parentheses aren't necessary, but I'm going to put it in parentheses, plus g of x, which is x plus 2. All right, so now I'm going to kind of go, all right, I'm supposed to add these. So the parentheses aren't necessary because you're not distributing through any kind of negative number or anything. So I'm going to actually just remove the parentheses from both binomials. And now I'm going to collect like terms. So 3x and 1x make 4x, and minus 4 and plus 2 make minus 2. So what's the domain of this combination? Well, this again is just another polynomial function, so I'm not going to linger there. I'm just going to say, well, it's all real numbers. All right, let's combine f and g by subtracting. So that's, I see subtraction, subtraction. So here's f of x again. Now we need a minus here, and then the x plus 2. All right, moving forward, all right, I can remove these parentheses because I don't see any powers or anything to multiply. So 3x minus 4, but behind this subtraction sign, I want to subtract everything that's in this quantity. And remind you, we could put in that negative 1 there and distribute. So that becomes minus x and minus 2. Now with all the parentheses removed, let's just combine like terms. So 3x minus 1x make 2x, I'll record it here, and negative 4 minus 2, so that's minus 6. The result of that combination is a polynomial function, so we're just going to put all real numbers for that domain. All right, C, okay, I'm looking at this going, that must be multiplication. So let me take f of x and multiply it by g of x. Well, I have multiplication here. I've seen this before. This is the FOIL method or distribution. So let's FOIL. So 3x squared. That product gives us 6x. The inside multiplied is minus 4x. And the last two terms multiplied is minus 8. I can combine some like terms. 3x squared. These two combine to positive 2x. And the minus 8, the constant, just comes over. So what's the domain of this combination by multiplying? Well, this is a polynomial. Again, there's no fraction here, no even root. So it's a polynomial. The domain is all real numbers. Okay, for example, D, when we're asked to combine, okay, f of x is 3x minus 4 all over x plus 2. All right, I don't need the parentheses. I'll just remove them. All right, and that's all we can do with that problem. Some students would say, can you divide out the x's? Unfortunately, no, you cannot divide out the x's. You can only divide out a factor if it belongs to every single one of these terms. And because there's no x here or x here, I can't divide out x's. So what's the domain? Well, notice this is not a polynomial function like these. So let's see, rational function, domain. Oh yeah, the denominator cannot be 0. So the values that would make your denominator 0 would be negative 2. Negative 2 plus 2 would be 0, and I can't have that. So my restricted x value from all real numbers is negative 2. All right, so on the next sheet, I have another combination example right here, and I'm going to actually modify it a little bit. For example 2, now f is a new function, it's the square root of x. And you know, I'm going to actually change g of x, and let's let that be another even root function. We're just going to put x minus 5 underneath the radical. All right, so we're going to add f and g. We're going to add these two. We're going to subtract these two functions, and we're going to multiply these two functions, and we're going to divide these two functions. All right, and determine the domain. So let's first start with finding the domain of the square root of x. Remember, we're not a rational function, even root. X has got to be greater than or equal to 0. So our domain is 0 to infinity. Okay, this is an even root function, so that means take the radicand. Okay, that value right there has to be greater than or equal to 0. You don't want a negative number. So add a 5 to both sides, so x has got to be a value for this function that's 5 or greater. And I can include 5 because if x is 5 and I subtract 5, I can find the square root of 0. All right, for part A, we want to add these two functions. So let's add the square root of x plus the square root of x minus 5. Instead of doing the work here, I knew that I wasn't going to be able to do anything with this, so I just went ahead and recorded the sum here. I can't add these together. When you're adding radicals, you can only add like radicals, and because x and x minus 5 are different, we just walk away from this problem. All right, so what's the domain? Well, the domain is the intersection of both these sets. So if we put a number line to both these sets, then I know 0 right here would be included, and I go this way. If I put this domain on this number line, then 5 is here, but I can't start this domain until x equals 5. So the intersection would be 5 to infinity. And let's think about why. If I chose some number smaller than 5, like 4, and I put 4 in for this part of the problem, I'm going to get a negative number underneath the radical. All right, what are we asked to do in part B? Subtract the two functions. All right, f was the square root of x, and g was the square root of x minus 5. I cannot collect any, these are not like terms. I can't do any kind of collection. We just walk away from this problem, and the domain is the same. Example C, we're asked to multiply f and g. All right, so I'm going to take square root of x, that's to multiply, and I'm going to multiply it by, I might want to put that in parentheses, square root of x minus 5. So I'm multiplying. And you can leave the problem like that, but there's actually one more thing you could do with that. You actually, on this one, you're not adding or subtracting, you're multiplying. You are actually allowed to multiply x times x minus 5 and put that underneath one radical. So you can leave your answer like this. This is fine too. Just kind of be careful of my math lab. They might want you to actually multiply these two together, or they actually might even want you to distribute in the x underneath that radical and get square root of x squared minus 5x. This domain's tricky. You're not going to be asked to do one like that. I'm just going to go ahead and record that domain answer, but don't worry about having to try and figure it out. I'm not even going to explain it. Okay, so let me see if I can remember. Okay, so again, don't worry about that. You're not going to be asked to solve that. But that is the domain for this combination when multiplying. All right, and the last thing we have to do is divide the two functions. So let's just take square root of x, that's f, and put it over square root of x minus 5. All right, we can with this is a great answer, but we can with this, when dividing, like multiplying, we can put one radical over the fraction x over x minus 5. Again, this domain is kind of tricky. You won't be asked to do anything like this. This domain actually happens to be 5 to infinity, but no bracket here. It's a parenthesis. If we think about that for a minute, okay, if we did allow x to be 5, then I'd have 5 over 0, and that's an undefined situation. So that's why we just want to remove the 5 from the possibility of the domain. All right, that's combination of functions. Now we need to look at composition. It's just another way of combining functions, but not using addition, subtraction, multiplication, and division. It's just a different method. All right, so the composition of the function f with g is defined as, so let's just look at the notation. So if we see this kind of notation, we have to know what that means. It's just like when you drive, if you see a stop sign, you know what that's telling you to do with notation or a sign. All right, so this is alternate notation. This little circle right here means f composed with g, and they're both equations that have x in them. Or I can write this what we call nested set of parentheses, and this is read as f of g of x. Okay, so what do we do when we see this notation? It doesn't mean to add, subtract, multiply, or divide. It's actually a substitution. And what's important to notice is that g is what we would call the inside function, while f is the outside function. So again, this is read as f of g of x. And you could either see it with this little circle here or this nested set of parentheses. Okay, so I've got an example here, and then we'll have a couple that we can do. But just reading through this example. All right, so for example 1, what if you're given the function f of x equals 5x plus 6, and g of x is this quadratic 2x squared minus x minus 1? If we're asked to find f composed with g of x, which is also equal to f of g of x, what we're asked to do is take the inside function, which is g, and put it inside of the f function. Again, we're not adding, subtracting, multiplying, or dividing. Let's put g inside f. So what I do, my brain, I go, okay, where's g? Okay, here's g, right here. We're going to put g inside f, wherever we see an x. So all of this is going to be replaced in, we're going to remove this x and replace it with the g function. So right here is the next step in our work. Okay, you can see the 5, it comes from that 5. Now all of this in brackets, or it could be parentheses, okay, is what g of x is equal to, 2x squared minus x minus 1. Go back to F, see that there's still a +6 and it has to be recorded. All right, now that we're here, is there more work that we can do? Yep, we can distribute the 5 inside, and in doing so, we'll get 10x squared minus 5x, which is here, minus 5, which is here, and don't forget the +6. Now we can combine. 10x squared gets carried over, 5 minus 5x gets carried over, but these two numbers when combined add to a 1. So this is your final answer. We put G inside the X that was in F because G was the inside and F was the outside. Okay, look at example B. Notice that they switched the G and the F. Now it's G composed with F. So now we read this as G of F of X. So the inside function is now F. So F's equation has to go into all the X's that are in G. So my eyes first go to F of X. Here's F of X. I have to put 5x plus 6 in for that X and 5x plus 6 in for that X, leaving everything else the same. So notice what comes up next. So here we are. So I'm putting F and G. So 2 comes down. X gets replaced with 5x plus 6. Don't forget the square. The minus sign comes down, but instead of X, build a parenthesis and put 5x plus 6 in here. Go back to G and notice you still have a subtraction of 1. Okay, this one's pretty involved algebraically. So from here over to here, notice that the 2 is still present. It matches with this 2. This is going to have to be expanded. This is 2 binomials, 5x plus 6 multiplied by itself twice. Now, what can happen next is you can distribute that negative inside here. So that becomes minus 5x. And this, when you distribute, becomes minus 6. And don't forget the minus 1. Okay, now let's take a look at this now. What work do we have to do? Well, we're going to have to FOIL these together first. Okay, so, and again, remember up here, you cannot multiply 2 inside this parenthesis because you got to do the power first before the multiplication. That's the order of operations. So that's why they expanded and put 5x plus 6 twice. Okay, now from here to here, the 2 is still out front, but notice that all of this right in this parenthesis came from the work being done off to the side by foiling these 2 binomials. So that's the presence here of these terms. Now notice here you have minus 5x, so we just return to collecting what else we had here, which is minus 5x minus 6 minus 1. Okay, so from here down to here, they're distributing the 2 in, getting 50x squared. I think they combined this and made it 60x, and 60x times 2 is 120x. And then 2 times 36 gives 72. Brought down the minus 5x, put those together, and this step made minus 7. Still have to collect 50x squared, that's gone. We've combined 120x and minus 5x, that's 115x, and 72 minus 7 produces 65. So kind of neat to note that, you know, depending upon the order in which you compose, if it's f of g of x or g of f of x, you're not going to get the same answer in most cases. All right, and one last example here before we have some of our own. C, notice that we have a number now. This is not x. So another way to write this is f of g of -1. There's a couple ways you can handle this. I prefer to put -1 inside g first, -1 in for x into the g equation first. Once I get that answer, I take that numbered answer and I put that into the f equation. Okay, so you can either follow this method or I'm actually going to look at how I do it in 2 steps. So g of -1. So let's go up to g. Everywhere you see x, replace it with -1, which was done here. Go right to your calculator, get 2. Now we have to find f of 2. 2 has to now go into the f function because it's on the outside. So now go to the f function, and everywhere you see x, you're going to replace that x with the new 2. Do the math on the calculator, and you get 16. Okay. All right, so if we go to our last page, finally, and look at what we have here, we have some examples that we can do. If you're comfortable and you want to attempt it on your own, again, I encourage you to take a brain break, try it on your own, and then come back and check to see how you did. All right, what's the domain of the composite function? It's the set of all x such that, this gets kind of confusing, x is in the domain of g, and then g of x is in the domain of f. So first ensure that the inside function is defined, and then examine the final function for any other restrictions. Okay, that's a lot to think about. I think we're going to kind of remove that from our equation this year, so to speak, and let's actually just find the compositions, and based on what we see, we can kind of report what the domain is. Knowing about polynomial functions, even root functions, and rational functions and what their restrictions are. All right, so here's our given. We've got f, we've got g. They're both polynomials, the domains are the same. We're asked to find f of g of x and its domain. Okay, f of g of x means g goes inside of f. So I first look for g, here it is, and I put this whole equation in for any and all x's in the f function. So f of g of x is equal to, where x is, I'm going to leave a parenthesis, so I can insert 2x minus 4. Don't forget the square, and then minus 1. So the outside function is present in this structure, but wherever the x was, I replace it with 2x minus 4. Okay, next step, I need to expand, write these two out side by side. And I still have the subtract 1. So let's FOIL and collect. I'm going to FOIL 4x squared minus 8x minus another 8x is minus 16x, and the last two terms multiplied is plus 16. And don't forget the minus 1. So I'm going to come from here to over here. So 4x squared minus 16x plus 15. By inspection, I know that's a polynomial, so my domain is all real numbers. All right, for problem number 4, f of x is square root of x. That domain is 0 to infinity. G of x is a polynomial, so its domain is all real numbers. They want me to find f of g of x. It could have been g of f of x, but they want f of g of x. This is inside g, and we're going to put it into the f. So g goes into f wherever we see x. All right, so in the f function, which is on the outside, I see the square root, so I need to get that going. And then x minus 3 will go in for x. So you actually remove that x and replace it, substitute in x minus 3. There's nothing we can do here, so that is the answer. Okay, but what's the domain? Well, it's not a polynomial function. It's not a rational function where we don't want to divide by 0, but we don't want a negative number underneath here. So take the radicand and make it greater than or equal to 0. Add a 3 to both sides. So any value, x value that's 3 or higher. Example 5, what's the domain for this rational function? Well, x can't be 0. We saw that on the first page. And we just did this one, so the domain is 0 to infinity. All right, let's do the composition f of g of x. I'm not sure why I'm just always doing f of g of x, but it's okay. So g's on the inside. So g's on the inside, so g goes in wherever that x is. So it's just 1 over square root of x. And there's actually nothing that we can do here to clean that up, so that's the answer. All right, this domain's a little bit tricky because we've got two things going on. We've got a rational function, and then we also have a even root function. So I think I'm going to deal with a rational function first. So that means the square root of x, that denominator, cannot be 0. Okay, so we've got to look at the rational piece first. So square root of x cannot be 0. So that means I'm going to square both sides. So x cannot be 0. Got it. However, that's just the rational function part of this. Let's also look at the even root part of this. Now, the other restriction on, now forget that we're dealing with the rational function. Let's just look at the square root of x. So the radicand has to be greater than or equal to 0. So let's build a number line. Let's put 0 on it. X can't be 0, so I've got to put an open circle. This says x greater than or equal to 0, but if I can't have 0 in one part of the problem, even if it says I can have 0 in the other part of the problem, I can't have it. So my domain is actually a parenthesis with 0 to infinity. I would encourage you to kind of test yourself and go, well, what if I did put a bracket here and included 0? Well, that means that you're going to be dividing by 0 in the fractional piece of this. Okay. All right, and one last thing I want to show you from the textbook, okay, is that you might have some problems where you're asked to interpret combinations and compositions from graphs. So this is page 311, and I just took I made a copy of this page. Okay, and I want to look at something with you. Okay, well, I can't see what's over here, but I guess I'll look at 84. Okay, notice that we've got a graph, and in this graph here, we've got the f of x function. Trying to see which one's which. The g of x function may be the lighter function. No, it must be this function. And maybe f of x is the lighter function. It'd probably be better looking at it in a textbook, but let's see if we can evaluate the difference. This is what this means. This is not a composition because we don't have nested parentheses. This says g of -2 minus f of -2. So let's go to the graph and let's go to where x is -2. And let's go up until we get to the g graph, which I think is the darker one. So g of -2 would be up here at this height. If I read it from the y-axis, that's 2 minus, now what's f of -2? Well, go to the same x, but go up until you reach the f of x graph, which I think is the lighter one. And read over here, go horizontally, that's 3. So 2 minus 3 is -1. All right, let's look at 86. 86 says that this is equal to g of 3, whatever that value is, divided by f of 3. All right, so let's go to the graph. Okay, the input x values are 3, so here's 1, 2, 3. So g of 3, which is the darker graph, is actually on the x-axis, so that's 0 on top. F of 3, so same 3 value. F, I'm going to have to come down until I get to the lighter graph. Its intersection is here, but when I read from the y-axis, it's -3. So 0 divided by -3 is 0. It's okay to have 0 in the numerator, but not in the denominator. Okay. All right, and we'll do a composition down here. So this is a little bit better. F is the lighter and G is the darker. Okay. So on 92, it says, let's compose f with g of 1. So another way to write that notation is just f of g of 1. So let's find g of 1 first. It's the inside function. Here's 1. G is down here. So down here, I'm at y equals -5. So I have f still, but g of 1 is -5. Now, this tells us that our new input value is -5. So now we got to go to a new x value, not of 1, but of -5, and find the f graph. So I go all the way up here, and when I get to this height, I read it from the y-axis, and that's 3. So my final answer is 3. So that's how you do combinations or compositions utilizing graphs. You locate the x values and you go up or down until you get to the y values, and those are all part of your answers. And then you finish with either the addition, subtraction, multiplication, division, or the composition.